Hi, thanks for joining everyone. I wanted to do this video on the topic of shallow history and deep history in a state machine. This is very interesting because what you may not realize is state machines can actually remember the previous state that they were in, and they can return to those states upon transitioning to a shallow history, which is what you see here, or by going back to a deep history, which is what you see here. So what is the difference between shallow history and deep history? We will run a few simulations of this, and you'll see how these react. Notice this shallow history here would be transitioned to by this signal 1, and what that means is it will return to the last neighboring state within this state, or the last substate within this composite state. Let's say, for instance, our state machine happened to be in substate 3, and then all of a sudden we received a system error. That would take this out of substate 3 and enter the error state. Of course, in that state, it would attempt a recovery. And then after receiving a signal 1, which is an abstract SysML signal, that really could be any type of an event that you would define as signal 1. If it were to go back to this shallow history, what that would mean is it would go back to this substate 3. We also have this deep history. So what that means is it'll go back to nested state or another substate, the last substate that it was in previously. So let's say, for instance, we made it all the way to this substate 6, and then we received that system error. After attempting the recovery, if we had a signal 2 sent, that would take it to this deep history, in which case it would not only go back to composite state 2, but also its substate that it was last in, which is substate 6. So that's a very interesting concept. Let's go ahead and run a simulation and you'll see what that looks like. So it's in the initial pseudo state now, but what we can do is send that signal 1, and then we'll send the signal 1 again. And this is interesting because this is really what differentiates state machine behavior from other behaviors, such as activity behavior. One thing to keep in mind is that state machines should be used for behavior where you have determined that your system responds differently to the same event depending on what state it is in. So notice here we have this signal 1 that transitions it to this substate 2, in which it would perform some behavior within this state. But then we also have a signal 1 down here that would transition it to a substate 6, in which it would perform a different behavior. So that's really what causes it to be considered state machine behavior versus simply an activity, is that it's responding differently to that same event depending on what state it is in. So let's go ahead and move down here to substate 3, and then we'll go all the way into composite state 2 by sending signal 6. Notice when it enters composite state 2, it immediately goes to substate 5. If I were to exit this state now by causing a system error, and then if we go back to our shallow history, what you'll notice is it should go back up here to composite state 2. And whenever it enters composite state 2, it goes into this substate 5 initially. However, let's go ahead and give it the signal 1 to transition to substate 6. Now, let's say I were to go and do that system error again. This time, keep in mind it was in substate 6. We'll go ahead and send this signal 1 to transition to shallow history again. And as you notice, instead of going back to substate 6, because it was a shallow history, it went back to the composite state and then immediately back into substate 5. So let's go ahead and do the system error again, and then we will transition to deep history. And in this case, what you notice is that it goes immediately not only back to composite state 2, where it would have started at substate 5, but it actually went back to composite state 2, substate 6. So that is really the idea of shallow history and deep history. And it's good to understand that state machines can be called even as a behavior in an activity, and that is something that can then be instantiated. And really what that is a way for a system to manage events. So notice we have all of these signal events, but there are other types of events that can cause transitions between states. So if you ever were to look in the specification for a state transition, notice we have the trigger here is a signal event. So that is considered event, and as I mentioned in SysML, a signal is something that is abstract. That could be a logical signal in this case. If we were defining a logical state machine, that could be something such as a power event or a system error. And then that's something that would further need to be refined in a physical architecture to show exactly what that logical event would be. But for this case, we're saying it is simply an abstract thing that we're calling signal one. However, there are other things that we can use besides signal events to transition state machines to other states. And notice here we have any receive event. That would really be any type of an event, any one of these other events that could occur, such as a call event. So a call event would be the call for an operation, and that can be used to trigger a state change. Notice we also have change event. So if we were to say change event, notice we now have the when with parentheses. And that could be when x is greater than y. That could be comparing values. That could be simply when something is equal to another value. So those are really when you start incorporating your value properties to say, hey, this is when a certain value may be some certain criteria, in which case it would transition to that state. We also have, of course, the signal event and then the time event. With time events, notice we have the option at, and that would be at a simulation time that is absolute. However, with time events, you also have the ability to check the box for is relative, which would make that after. And you've seen that in other videos, I'm sure. I've seen Salius has some videos out there where he uses this relative time event, or you might want to define something such as after 3 seconds, then transition to another state. And of course, these can be combined with guards. So you can not only have the event that it's looking for in order to transition, but you could also have a guard that might say something like value 1 greater than 5. And of course, that could be defined in the block that executes this activity as a value property, in which it would be looking for that in order to inhibit it from transitioning to another state. So even after 3 seconds, if this value 1 were not greater than 5, this would not transition to substate 2. So I hope this has been helpful. I want to reiterate another time that state machines are something that can be very useful for behaviors that you determine are event-driven, where that system is responding differently to the same event depending on what state it is in. And that is different than what you would model in an algorithm, where you may have an activity or an activity diagram that specifies a certain set of criteria and it's making decisions, and you may have control loops and things of that nature. So let me know if you guys have questions on this. Thanks for watching.